Right, let's get going. Continuing with the relaxation theory today. This time we'll do a theory that is, on the one hand, more general than Redfield's theory, in that it avoids some of the hand waving and in principle applies to various specific modes of rotation or specific modes of translation in a more general sense. But it is, on the other hand, also considerably harder to use, and in particular considerably harder to compute than Redfield's theory in practice. So, generalized cumulant expansions, and the theory is making the basic assumption of a rather different kind. If you remember, when we derived Bloch-Redfield Banksness theory, we had d by dt of our density matrix was minus I h superoperator the density matrix, and that depended on time. And then we said that if we have a stationary and a stochastic component in our Hamiltonian, so we have h0, which is in some sense large, and we have h1, which is in some sense small, centered, and depends on time in a random fashion, then what we could do is take this equation, transform it a little bit, then take the ensemble average of both sides, and with a few extra approximations and assumptions, we got the rest of the theory. Now, so this, as it were, means averaging, dynamical averaging, on the level of the differential equation. So we take this entire picture, and we apply some well-behaved ensemble averaging to it, and then see what happens. And it works reasonably successfully, so this is Bloch-Redfield Banksness theory. On the other hand, what the generalized cumulant expansion formalism, as we'll see, does is it first solves this equation, and we know what the solution is. We derived it at some point in term 1. This is the so-called time-ordered exponential. I'll just put the little O in there to remind us that this is a time-ordered thing. Integral from 0 to time t minus I h double hat of t prime t t prime, and then rho 0 in here. What this prescription actually says is we should be taking care when evaluating this propagator how we count and order the Taylor terms, or equivalently, I guess, for practical purposes, that means that the only way to compute it is to slice up the time in sufficiently fine slices so that the Hamiltonian could be assumed stationary in each slice, and then apply them sequentially. But what happens if h is stochastic? That is, its random nature occurs on the time scale of, let's say, molecular rotation. So that would be femtoseconds. And so this becomes essentially incomputable, even though it is, strictly speaking, an exact solution. But, well, we've got this noisy Hamiltonian. So in Redfield's theory, we got around it by averaging out very fast motion and replacing them with the correlation function of those motions. What we will do here is do a similar averaging, but we will do that averaging not on the level of the differential equation governing motion, but on the level of the solution to the differential equation that governs the motion. Which is arguably a better thing to do, because necessarily here we had to assume a few things about this process, and how it behaves in time in particular. And really, to be a part of a differential equation, it has to be extremely well behaved. There are fewer such restrictions here. This is already an exact solution, and the one thing we need to do now is to average that solution over the ensemble, and as you'll see in a moment, there are considerably fewer assumptions that one needs to take in that case. So if we take this and apply an ensemble averaging to it, then the resulting formalism became known as the generalized cumulant expansion. But before I go deeply into the actual spin dynamics, quite a few mathematical introductions are in order, because neither in chemistry nor in physics, nor I guess in most mathematics departments these days, are cumulants a part of the undergraduate program. so we will have to introduce them and actually go back to quite a lot of statistics in order to be able to use it later. Right, so let x be a stochastic variable, so random variable, and every time you look at it, it has a different value, and let px be the probability distribution of that value, giving, when you take an integral over a tiny slice, the likelihood of x being in that particular tiny slice. What we will define now is something called nth moment. An nth moment of x is an average of x to the power of n. And when we take an average, we just take the value of whatever function we are averaging, multiply it by its probability density, and integrate all possible values. So this would be an integral over whatever domain x is assumed to take, infinity minus infinity, complex surface, and so on, but just an integral. We shall assume minus infinity to infinity for the real axis, x to the n p of x dx. And the reason why it's called moment is it is related to the various skews and tilts that you find in this distribution. The zeroth moment is just equal to 1 because an average of 1 is 1. The first moment is the usual average, just x. The second moment is related to dispersion, how broad the distribution is. The third moment is related to how skewed it is, and so on and so forth. And it is oftentimes convenient to describe these distributions in terms of the various moments. Some of them can be measured directly from the experimental data, and so on. The next thing we'll introduce is something called the moment generating function, and why it's called that way will become clear in a moment. So, moment generating function. It is the expectation value of e to the kx of such an exponential. And if we just follow it through, it will be, as per the definition, an integral from minus infinity to infinity, e to the kx, p of x dx. Now I will expand the exponential in the Taylor series. It will be the integral minus infinity to infinity, a sum from n equals 0 to infinity, 1 over n factorial, then k to the nth x to the nth, then p of x dx. So what we can now do is take the sum and a few other things out of the integral. So we will have a sum from n equals 0 to infinity, k to the n over n factorial, and then an integral minus infinity to infinity, x to the n p of x dx. And here you can actually recognize that definition of a moment. So we can further rewrite that as a sum from n equals 0 to infinity, nth moment, x nth over n factorial, then k to the nth. So you see what happens if we take this and it's averaged over x, so it is now a function of k, and take this as a function of k and expand it in the Taylor series as a function of k, then the moments occur in the expansion coefficients. So it's the moment and then n factorial, but you know extremely well what should be occupying this space in the Taylor series. It's the derivative of the function, and so what we conclude is that the moments are in fact the derivatives of the moment generating function. More precisely, x nth moment, so nth moment of x, is dn by dk to the n of the expectation value of ekx evaluated at k equals 0. And this is the reason why the expectation value of ekx is called the moment generating function. It is because it actually is generating those moments in the same way as, for example, Chebyshev polynomials are generated by the corresponding generating functions, or Legendre or Laguerre. You've seen quite a few generating functions in your life, I think, where a particular polynomial is related to a derivative of something complicated, and that is in fact a very easy way to generate those polynomials. And in a similar spirit, the derivatives of this function evaluated at a particular point in K just happen to be equal to these moments. Right, so okay, we've got the moments. What we'll now introduce further is something called cumulants, but before we do so, I will sketch out the physical rationale for why we're doing it, just so that it doesn't look like I'm pulling this out of a bag. What we've got, if you remember, in that formulation of relaxation theory that's based on the solution to Schrödinger's equation, is we had this exponential of minus, ordered exponential of minus integral from 0 to time t, I, there, h double hat of t dt prime was ensemble average. So what we wanted to do is express this, which would be a propagator of some kind that is applied to a physical system. Because it's a propagator, it's the generator of the corresponding propagation semigroup. It wouldn't be a group in there because it's not unitary, but it would be a semigroup. So hopefully, and we don't really know, this stuff should be expressible as minus I L T, where L is some unknown operator. It would depend on the assumptions, it would depend on the system, but hopefully once we've built a successful relaxation theory, we ought to be able to find some kind of stationary thing that's not too complicated, that would have that kind of relationship. So what we are looking for is L, and therefore we are looking, strictly speaking, for the log of this thing. So you see, we are looking for the logarithm of the expectation value of some exponential. And this is the physical rationale, so when we're now moving to cumulant and cumulant generating function, you will see that they in fact take us, at least some way, towards that goal. So now the definition, a cumulant generating function is defined as the log of the moment generating function. And you can see immediately where I am coming from. Yes, this is a vastly simpler case. We only have a single variable. That single variable is a scalar, but at least it's the kind of functional form that we eventually hope to achieve at the very end. Okay, and similarly, if we have a cumulant generating function, its derivatives must be called cumulants by the logic of the things, and so that is the definition of a cumulant. And there's quite a lot of different ways of denoting them, various notational conventions. What I will be using is the double angular bracket. So that n's cumulant will be, as the name suggests, dn by dk to the power n of log ekx evaluated at k equals 0. So these are cumulants. And as you see, we're getting closer. That's called the generalized cumulant expansion there for a reason. We'll have to generalize these things in a moment. Alright, well, one important thing is, of course, moments are relatively easy to relate to cumulants, because once you take this derivative of a log is just 1 over, and then the derivatives of this expectation value pop up, and we know what they're equal to. So it is possible to express cumulants with relative ease in terms of the corresponding moments. And for that, I will just wipe the board and do a couple of illustrative calculations just by hand. So this, unfortunately, is a part of mathematical statistics that's not very often on any kind of undergraduate course these days. So we have to introduce it. Right, so why don't we compute the first cumulant of x? So double bracket x ought to be equal, as the definition says, to d by dk of log ekx computed at k equals 0. Well, d by dk of a log is 1 over the expectation value kx times the derivative of the function, so d by dk of ekx, all of it computed at k equals 0. So now that we substitute k equals 0 here, what will happen is the index will become 0, the exponential will become 1, ensemble average of a constant is just equal to that same constant, in this case 1, so this simply disappears. And what we've got is d by dk of ekx at k0, so that just happens to be equal to the moment of x. Of course, that's so simple only because this is the first cumulant. Life becomes considerably harder if we take the second cumulant. I'll just do it as an illustration, and I've listed cumulants up to order 4 in your handout for the brief to repeat. So x squared cumulant will be d2 by dk squared of log ekx at k equals 0, and that's an exercise in differentiation. So taking the first derivative, d by dk of 1 over ekx d by dk ekx, then taking the second derivative, it will be a product. So term number 1 minus 1 over ekx squared d by dt ekx also squared plus 1 over ekx d2 by dk squared ekx, all of that computed at k equals 0. And that would be, once we've done that, the expectation value of that is 1, so this just disappears. This thing in the brackets is just the first moment. This disappears. This thing in the brackets is the second moment. So what we have is, in the end, second moment minus first moment squared. Here, familiar expression known in the trade as dispersion. Right, so here's how to do it, and so we can continue forward, and as far as we like, really. It's a fairly pointless exercise at this point, because this is just mathematics without any obvious physical meaning to it. So to summarize, and if, for example, we just put k to 1, as we will eventually have to do, we have just derived the following, that for a stochastic variable x, the expectation value of the exponential of it can be expressed in terms of moments of x as n from 0 to infinity x nth over n factorial. Perhaps an easily expected thing. You just take an expansion of the exponential and take the average of both sides. But the less obvious thing, this is also equal to the exponential of the sum from n equals 0 to infinity of cumulants of x divided by the n factorial. And this is something that we will be taking advantage later of. Right, so this was the case of a single stochastic variable. It is never the case in physics that we simply have just one random scalar. We usually have a random vector or a random matrix or random goodness knows what. So the next level of generality will be to consider a random vector. Now we could have just started with a random vector and built it directly up from there, but really by way of gentle slope, this is bad enough. So we will now gently move over to vectors. So if we have a vector of stochastic variables, so x1, x2, and so on, with the joint probability p of x1, x2, and so on. So those will be the vectors, and this will be the probability density of hitting that particular point in whatever space these vectors are living in. Then the moment generating function is the direct generalization of z. So mgf in that case would be the expectation value of E of an arbitrary linear combination of these variables. So it will be k1 x1 plus k2 x2 plus so on, where k1, k2 and so on are just arbitrary numbers, much like the variable k here was an arbitrary number. Then the joint moments of these things will be similarly defined in terms of derivatives of that thing. So if I take a moment of x1 to the power alpha 1, then x2 to the power alpha 2, and so on, and take an ensemble average of that, what we will have is the moment, and that would be the corresponding derivative of the moment generating function d alpha 1 plus alpha 2 plus so on by dk1 to alpha 1, dk2 to alpha 2, and so on of our moment generating function k1 x1 plus k2 x2 plus so on. Right? So this is only, I guess, notionally more complicated. Instead of an individual variable, we now have a linear combination of variables. And it is similar in the case of cumulant generating function. So just like MGF was that, CGF will be the log of it. So log of E k1 x1 plus k2 x2 plus so on. And similarly, the joint cumulant with whatever powers of x we have in there, x1, alpha 1, x2, alpha 2, and so on, will be the same bunch of derivatives of the cumulant generating function. So I'll just skip the writing in here because you have it all in your handouts. Now, the task of relating cumulants to moments becomes a bit harder, but again, only technically so. So I've listed a couple of examples in your handout, and I'll just go through a couple of them by hand for illustration purposes. But it is essentially the same. So by using the definition of the cumulant generating function, it is possible to express moments in terms of cumulants and vice versa. It's just a matter of, really, by this time of typing this into Mathematica, getting the correct patterns set up and just letting it get on with it. There is nothing too hard about differentiating. In fact, differentiation, unlike integration, is formalizable. You can, in principle, teach a sufficiently sophisticated monkey to do it, or a machine. Whereas integration, for it, there is no, intrinsically no general algorithm to actually do it symbolically, so it's considerably hard. Right, so first, cumulant of just x1 if the vector is just a one-element vector, as we of course expect, is just equal to the moment of x1. But life gets a little bit more interesting when we have two elements in that vector. So let's say we've got a cumulant of x1 times x2, where these are the two variables in a random vector. So then this will be equal to, as per the definition, d2 by dk1 dk2. So this occurs once and that occurs once of the cumulant generating function e k1 x1 plus k2 x2, computed at k1 and k2 equals 0. Well, we just need to take those derivatives. So I'll differentiate with respect to k2 first. It will be d by dk1 of 1 over the bracket, and then d by dk1 of the bracket. Now the derivative with respect to k1, this will be minus 1 over bracket squared d by dk1 bracket times d by dk2 bracket plus 1 over bracket d2 by dk1 dk2 of that bracket, all computed at k equals to 0. Well, as per the arguments that we already saw, the expectation value of this and the expectation value of this is just equal to 1. This is the cumulant of x1, this is the cumulant of x2, the moment of x1 and moment of x2, and this is the joint second moment. So what we will have is the moment of x1 times x2, so the expectation value of the product minus the product of just the averages. So, okay, that looks good. So we can in principle just continue it. I gave you another term in the handout, but it is time to try and generalize this to the case where it actually starts making sense for magnetic resonance. So the next thing we will prove is something that appeared already in the context of spin dynamics in Kubo's work in, I think, 1968 or thereabouts, where the task was set up of actually doing that relaxation theory by ensemble averaging the time-ordered exponential. Well, if we have a time-dependent Hamiltonian, it can be specified as a very long vector of Hamiltonians with infinitely small spacing. So what we will now do is try and compute the general case of an integral under the exponential rather than the sum. So what we so far had was an n-element vector and random vector, and you sum over the elements, and then in the limit, where the vector is infinitely long and the spacing is infinitely fine, you get the integral, the definition of the Riemann integral. So let us now take that limit and see what happens. So for that, I will need to remind you the expression for the n-dimensional Taylor series. So if we have a function of x1 and all the way to xn, where n is the number of variables, and we would like to expand it into a Taylor series, what will happen is the Taylor series will be just a combination of every possible derivative, partial and mixed, divided by the corresponding factorials, and then there will be the products of various variables in the same order as derivatives occurred in the derivative. So if we have n variables here, we will have n sums over powers with respect to the corresponding variable. So alpha 1 from 0 to infinity, all the way to alpha n from 0 to infinity. We will then have a bunch of factorials coming out from the corresponding derivatives, alpha 1 factorial times all the way to alpha n factorial. There are no convenient expressions for this in terms of so-called multi-indices. You can look it up in Wikipedia what that means. But really, in our case, we actually need to do it the difficult way. And then the corresponding mixed derivative, d alpha 1 all the way plus all the way to alpha n, then d alpha 1 x1 times all the way to d alpha n x n of the function, computed in our case at 0, so where all xi are 0, and then x1 alpha 1 times all the way to xn alpha n. So this fairly scary expression is a multi-dimensional Taylor series, just the usual extension of an ordinary Taylor series for the multi-dimensional case. So what we will now say is, okay, let our function here be the cumulant generating function for some random vector. So this will be replaced by the log of the expectation of an exponential of k1 x1 all the way to kn xn. And we will be computing this series, but we know what the derivatives are. The derivatives are cumulants, so it gets a bit simpler. So will be a sum from alpha 1, 0 to infinity, all the way to the sum of alpha n 0 to infinity, and there we will have our cumulants, double bracket, x1 alpha 1 times x n alpha n, double bracket over that bunch of factorials, alpha 1 factorial all the way to alpha n factorial, and there will be k1 alpha 1 all the way to kn alpha n. So we have expanded our multi-dimensional cumulant generating function in terms of the individual joint cumulants of those random variables. Well, now what we need to do is to observe that as we make our discretization finite and we make the number of points infinite, the sums, these ones, become integrals. And more specifically, the definition of a Riemann integral, an integral from a to b f of x dx, just happens to be equal, I'd rather say f of t dt, f of t, because we'll be dealing with time. dt is the limit when the fineness of that discretization actually goes to 0, so it becomes infinitely fine. So maximum of our discretization steps, delta t, goes to 0, that's the limit of the sum from I equals 1 to the number of points in the discretization, f of x I delta t I. So that is just, the integral is the limit of the so-called Riemann sum. That is the standard part of, I guess, an undergraduate calculus course, at least in the physics departments. So why don't we take this limit and apply it to this expression? What will happen is, instead of the exponential of a sum, we will have the exponential of an integral. Instead of a sum here, we will have an integral, so we will have an n-fold integral, and everything else will just continue as it goes. So what we get in the end is the log. The other thing that we'll need to notice is, of course, there will be multiple powers here, and multiple powers of delta t's as well. But as we go to the limit, only terms which are linear in delta t will actually survive. If the term is quadratic, it will have a different order of smallness, so it will vanish when we take the limit. So, bearing all of that in mind and taking the corresponding limit, we get something known as the Cool Theorem. So, a log of an exponential of an integral from a to b x of t dt will be equal to a sum from n equals 1 to infinity, 1 over n factorial, then integral from a to b dt1, integral from a to b dt2, and so on, integral from a to b dtn of the cumulant x of t1, x of t2, all the way to x of tn. Small n in here. So this is the continuous limit of this. And you see we are getting slowly closer towards our original stated objective of finding ensemble averages of such exponentials. One last thing that we need to worry about is, you see, while they are scalars, it's relatively easy because all scalars commute and we don't have to worry about time ordering here. but if we had non-commuting things, this would have been taken in time order. So we better translate it to a form which doesn't require time ordering. And that was discussed in the 8th, some pigeons over there, was discussed in the 8th lecture of this course, 2 terms ago now, where we take the integrals not simultaneously but sequentially, then the factorial disappears, and so the non-time ordered version of that, just in case for now, will be equal to a sum from n equals 1 to infinity, integral from a to b dt1, but then integral from a to t1 instead of b dt2, and integral from a to t2 dt3, and so on, an integral from a to tn minus 1 dtn, and then the same cumulant in here. Right, so this doesn't require time order whether or not the variables commute. So we just keep the natural order that there was under those cumulants. And so now what we need to do is to take the final step and make this x into a Hamiltonian, and then we would actually be able to express this propagator, the logarithm of that propagator, so the generator of that propagation, in terms of something that actually by now looks vaguely familiar. You remember we had to take ensemble averages of the products of Hamiltonians in red field theory. And as you'll see, we'll arrive at an almost identical expression to second order, but of course we will be able to take it to further orders as well. And also note that so far we haven't actually made a single approximation here. This has all been exact mathematics. So generalized cumulant expansion, even though it's a bit more complicated, is also a bit more sound than the more physical theories, or I guess the more physically motivated theories. So the next thing to do is to take this integral and try actually move into our usual Hamiltonian quantum mechanics. So I will make the usual, I will do the usual things. I will say that okay, we've got some big interactions in the system that we don't really want to bother with, and so we do a rotating frame approximation, or well, rotating frame transformation, it needn't be approximate, with respect to those large interactions. And so the only thing we need to deal with is then the interaction Hamiltonian, which we will also assume to be centered. That is, the ensemble average with the straight, the first momentum is 0. If it's not 0, we can subtract it out and put it into H0, so that doesn't lose us any generality. So, in the rotating frame picture, what we have is d sigma, where sigma is the rotating frame density matrix, by dt, would be minus I Hamiltonian, the interaction, the H1 commutation superoperator in the rotating frame as a function of t, sigma of t. So that's our good, old, nice, standard rotating frame derived from Neumann equation. You remember from red field theory is the first step we took was to formally integrate either side, so it would be sigma of t would be equal to sigma of 0 minus I integral 0 to t h1r of t sig t prime sigma t prime dt prime. Just makes it integral equation, nothing changes. But if we do it multiple times, as we did in our lecture 8, then what we will eventually obtain is something that is the expression for the time ordered exponential. So sigma 0 plus sum n equals 1 to infinity minus I to the power n. And so just these nested integrals as we continue resubstituting this expression into itself all the way to infinity. So integral 0 to t dt1, integral 0 to t1 dt2, all the way integral 0 to tn minus 1 dtn, and then h1r of t1, h1r of t2, and finally h1r of tn applied to sigma 0. So you see, from just rewriting the little von Neumann equation, we get the kind of expressions that actually look pretty similar to what we have just observed in the case of the generalized cumulant expansion. So this, as you know from lecture 8, and if you don't remember, look it up please. It's on video, so you can just watch lecture 8 all over again. This defines a time-ordered exponential. So sigma t is exp ordered minus I integral 0 to t h1 r t prime dt prime applied to sigma 0. And once we do the ensemble average of this, we arrive at the requirement to compute the ensemble average of this exponential. So ensemble average of the density matrix is just what we want. Because every system in the ensemble starts from the same initial state, there is no average necessary for sigma 0. So we arrive at the ensemble average time-ordered exponential applied to the initial state. And from Kuba's theorem, we now know how to handle the ensemble averaged exponentials. So finally, after we plug everything together, what we will obtain is what's known as the generalized cumulant expansion for the time-ordered Hamiltonian exponential. And because we know how to express cumulants in terms of moments, it will eventually be expressible in terms of simple basic averages and correlations that we know how to compute. So finally, ensemble average of a time-ordered exponential of minus I integral 0 to t h1 t prime dt prime, commutation superoperator here, is equal to the exponential of, so ensemble average has disappeared, it's now inside a sum from n equals 1 to infinity minus I to the power n integral 0 to t dt1 integral 0 to t1 dt2 all the way to integral 0 to tn minus 1 dtn. Cumulants h1r of t1, h1r of t2, all the way to h1r of tn. And because all our t's, by virtue of having those upper limits, are in time order automatically, it is actually already enforced. So why don't we look at a couple of initial first terms in this expansion. So let's take the sum to n equals 1, then to n equals 2, and see what we get. So when we take this sum, let's call it, well, let's call it k. So it will be k0 plus k1 plus k2 and so on, depending on the order it has in the exponential. So k1 will be just the first cumulant, not even integrated. But the first cumulant, as we saw, is the same as the first moment, so just the average. And by our assumption, we have subtracted the average out of our stochastic Hamiltonian, so the average isn't 0. So our first term there is 0. Our second term, k2, would be the exponential, but I'll just skip the exponentials here, minus I squared integral 0 to t dt1 integral from 0 to t1 dt2 of the cumulant average of h1r t1, h1r t2. Well, let us expand this cumulant average. You remember that we just did it a moment ago. This was equal to the moment, joint moment, h1r t1, h1r t2, minus the product of the separate moments. But the separate moments are 0, because this averages to 0. So in fact, we can simply replace this cumulant with the corresponding moment, so they are single brackets instead of double brackets. And behold, this is Redfield theory. Yeah? So it is, in fact, once you differentiate it to get as a propagator rather than as a generator rather than the propagator, so differentiate it once, you will have the familiar integral from 0 to a time of what you can see is, in fact, a correlation function between time t1 and time t2. And then you say, well, okay, the correlation function is assumed to decay quickly, so we can extend this to infinity. And this is supposed to be stationary noise, so it only depends on the difference in time. And write it translated to 0, integrate from 0. And there you get the usual equation for the Redfield-Punksness relaxation theory. So, as you can see, and we can probably expect that because that theory is very successful, it is in fact a special case of the generalized cumulant expansion. So once you get it all the way to here and then make all the assumptions that Redfield made, you actually recover the Redfield theory, which is reassuring. But we have further terms. So we have K3, which will be minus I this time cubed. And if you go through the relationship between the third cumulant and the third moment, you actually find that indeed only the one term survives. So we get integral from 0 to t, dt1, integral 0 to t1 dt2, integral 0 to t2 dt3, and then just a moment. h1r t1, h1r t2, h1r t3. And so to take relaxation theory to third order, the only thing we need to do is to compute triple correlation functions and integrate them twice. So what we had in the case of Redfield theory was just a single operator valued Fourier transform, which we had to compute with some difficulty, but we managed. In this case, it would be a two-dimensional superoperator valued Fourier transform with respect to two time parameters, and extra assumptions will have to be made as to how those correlation functions behave, and extra derivations would have to be carried out to actually determine what those correlation functions are, but at least this is a standard thing that can be then taken forward, and so on. So, interestingly, third order term is the last term that's actually simple. When you go to fourth order, it wouldn't just be the fourth joint moment, it will be the fourth joint moment minus a bunch of the products of second joint moments. It's in your handout, it's a fairly lengthy expression, and then a three-dimensional superoperator valued Fourier transform. So, you see the theory is quite beautiful in that it gives you the complete picture. And it doesn't make, essentially we haven't made any assumptions in here. So far as the truth goes, this is the truth. How you compute that will of course require assumptions later on, but the theory has the beauty of generality. It also has the beauty of being essentially incomputable. I mean, there's hard enough time computing a superoperator Fourier transform here. Spinach does it, the software package, but it takes its time. You can imagine what's it like to compute the two-dimensional version where you have to store all those superoperators before integrating them over. So, essentially computability runs out about here. So, this is computed routinely, and to be honest, I've never seen this actually being used. Because generally this is good enough for most practical purposes, for proteins and such like. And if you are into really slow motion and really paramagnetic stuff where all interactions are very strong, you are better off using the stochastic Liouville equation formalism, which we will be treating in the next lecture. So even though this is a beautifully general theory which has its place in history, as it were, to be honest, in 10 years of doing magnetic resonance, I've yet to see it being seriously used. We have used the existence of this term once to build the error estimate for the accuracy of this term, but that's about as much as was really practically necessary. So it has its place in history, it allows you to understand Redfield theory considerably better, but it would be a heroic effort to really use this theory beyond third order. By the time you're prepared to make that kind of effort, you really should be using the stochastic Liouville equation, which is the topic of the next lecture.